We've got some updates. Check out these new images that show 3I Atlas in a whole new light.
For months, scientists couldn't see it. The true nucleus of 3I/Atlas, the actual solid body at the heart of this interstellar visitor, was buried beneath a blinding cloud of gas and dust that no telescope could penetrate. Then James Webb did what nothing else could. Using post-perihelion infrared data, it cut through the noise and captured the nucleus directly. Crisp, defined, and measurable for the very first time.
I was told by two sources that in fact NASA plans to release those images in a few days in the middle of next week.
The image that came back stopped researchers cold, because what Webb revealed didn't match the models. It didn't match the predictions. It didn't match anything built around this object over the past year. The nucleus was finally visible. And everything scientists thought they understood about 3I/Atlas, its size, its chemistry, its motion through our solar system, was suddenly, quietly, catastrophically wrong. What the coma was hiding. Before we get to what that number means, you need to understand what made it so hard to find in the first place. From the moment 3I/Atlas was detected racing into our solar system, it wore a disguise. That disguise was a coma, a vast, luminous cloud of gas and dust surrounding the solid body at its core. As the object heated up approaching the sun, volatile materials boiled off its surface, scattering sunlight in every direction. To ground-based telescopes, 3I/Atlas appeared as a bright, diffuse smear, beautiful, dramatic, and completely useless for measuring the actual object underneath. Here's the catch. A coma doesn't reveal truth, it obscures it. The coma reflects current activity, how aggressively a comet is venting material right now, which can spike and fade unpredictably depending on surface conditions, rotation, and proximity to the sun. What scientists actually needed was the nucleus itself, the solid permanent body underneath all that glow. Because the nucleus is what carries the object's real history. Its mass, its structure, its composition, those are the things that tell you where something came from and what it actually is. For months, that information was simply unavailable. Astronomers were forced to work with indirect estimates. They modeled how much light the object produced, made assumptions about its reflectivity, and reverse-engineered a rough size from those calculations. Those models pointed toward a modest nucleus, something in the neighborhood of 1 kilometer across, compact, light, manageable, and every theory built around 3I/Atlas, every explanation for its motion, its chemistry, its behavior, rested on that foundation. James Webb was designed precisely for situations like this. As an infrared telescope operating in the cold vacuum of space, it doesn't compete with Earth's atmospheric noise or thermal interference. It detects faint heat signatures that visible light instruments simply cannot access. More importantly, it can cut through surrounding gas clouds to find what lies beneath. After 3I/Atlas reached perihelion, its closest point to the sun, and began pulling away, its activity gradually dropped. The coma thinned, the noise cleared, and Webb looked directly at what had been hidden all along. In the weeks leading up to the observations, the scientific community was cautiously optimistic. Post-perihelion imaging had worked before for other active objects. The expectation was that the coma would thin enough to allow a clean size measurement. That size would feed into updated mass estimates, and those estimates would finally let scientists adjudicate between competing theories about 3I/Atlas's nature. Some researchers thought it would prove to be a fairly ordinary, if exotic, interstellar comet. Others suspected something unusual about its composition, but expected the core to be roughly in line with earlier brightness-based guesses. Nobody was braced for what came back, and here's what nobody expected. The number that appeared on Dr. Meach's screen didn't just revise the earlier estimates. It demolished the framework those estimates were built on. The nucleus is far larger than anyone expected. When the post-perihelion Webb data was fully processed, the first measurement to emerge, and the one that sent shockwaves through the scientific community, was size. The nucleus of 3I/Atlas is approximately 2.6 kilometers in diameter, with uncertainty ranges suggesting it could reach close to 3 kilometers. Think about what that actually means. At first glance, the gap between 1 kilometer and nearly 3 might not sound dramatic, But in physical terms, that difference isn't just significant, it's transformative. Here's why. Mass doesn't scale in a straight line with size. When you triple the diameter of a spherical object, its volume, and therefore its mass, doesn't triple. It increases by the cube of that factor. Triple the diameter, and you get roughly 27 times the volume. For a body that scientists previously assumed was around 1 kilometer across, moving to nearly 3 kilometers means they were dealing with an object potentially 20 times more massive than their models allowed. 20 times more massive. Let that sit for a moment. Every explanation that had been constructed around 3I/Atlas, every theory about how it behaved, why it moved the way it did, how solar forces affected it, was built on a mass estimate that could be off by a factor of 20. The moment the new size came in, those explanations didn't just weaken. Many of them collapsed. The comparison with previous interstellar visitors makes this even more striking. 1I/Oumuamua, the first confirmed interstellar object, was estimated at roughly 400 meters on its long axis. 2I/Borisov was more comet-like and measured perhaps 1 kilometer. Both fit comfortably within existing models, small, relatively light, behaving mostly as expected. 3I/Atlas is in a different category entirely, not just slightly larger than its predecessors, but massive enough that it introduces an entirely different class of problem. Processes that work predictably on small comets don't necessarily scale. Forces that can nudge a lightweight nucleus around become nearly irrelevant when applied to something carrying this much inertia. But here's the problem, and this is where it gets genuinely strange. If this object is that massive, why does it still move like it's light? If you want to be the first to know when the next Webb data drops on 3I/Atlas, subscribe now, because this story is nowhere near finished. The motion problem that doesn't add up. Let's talk about non-gravitational acceleration. It sounds technical, but the concept is straightforward. When comets heat up near the sun, ice converts to gas. That gas escapes from the surface, and the escaping stream exerts a gentle reactive force on the nucleus, like a tiny thruster firing continuously. For small, lightweight objects, this effect can measurably alter the trajectory over time. Scientists call this non-gravitational acceleration, and it's well documented in comets throughout the solar system. It's one of the tools they use to trace where comets came from and predict where they're going. 3I/Atlas showed this kind of acceleration. Its path through the solar system didn't follow a pure gravitational curve. Something was pushing it, and outgassing, gas escaping from a heated surface, was the natural explanation. That explanation worked when the nucleus was assumed to be small. It stopped working the moment Webb revealed the true size. Here's the catch. A nucleus approaching 3 kilometers in diameter, carrying the mass that implies, is not easily nudged by escaping gas. Physics is unambiguous on this point. To produce measurable non-gravitational acceleration on an object this massive, you would need an extraordinary, sustained, and violent release of gas. The kind that would be visible, dramatic, and unmistakable in observational data, the kind that would leave the surface looking torn apart, the kind that would produce brightness spikes far beyond anything observed. But that's not what astronomers saw. The surface activity of 3I/Atlas, while unusual in other ways, was not at the level required to move something this heavy. Not even close. The object moves like it weighs far less than Webb says it does. Both facts are supported by solid data, and they refuse to reconcile. Scientists explored alternatives. Some suggested the gas might have been released unevenly, a single active region firing like a directional thruster rather than distributed venting. Others considered the possibility of internal structure playing a role. If 3I/Atlas is not a uniform, solid body, but something closer to a loosely bound rubble pile, its actual bulk density could be far lower than the external diameter alone suggests. A porous nucleus with lots of empty space inside weighs much less than a dense, solid one of the same external size. And here's what that would mean. The Webb size measurement could be accurate, and the motion data could be accurate, and both could be pointing to a single, deeply strange conclusion, that 3I/Atlas is large but extraordinarily light for its size. A massive shell of loosely packed material traveling between stars. That would help explain the motion. But it would immediately raise a harder question. How does a loosely bound structure survive thousands or millions of years of interstellar travel? Radiation, cosmic ray bombardment, thermal cycling. The journey between stars is brutal. A loosely packed object would need to be far more durable than its structure suggests. Or it would need to have formed very recently, very nearby, under conditions we haven't yet identified. Every answer with 3I/Atlas tends to open a new door. And then the chemistry arrived and made things considerably stranger. Chemistry that breaks the pattern. James Webb is not just a camera, it's an infrared spectrograph, a machine that measures how different wavelengths of light are absorbed and emitted by specific molecules. From those signatures, it can identify what a substance is, how much of it is present, and in some cases, how it's behaving at a molecular level. What it found in the coma of 3I/Atlas was not what anyone expected. Start with the basics. Early in 3I/Atlas's approach to the Sun, carbon dioxide was the dominant gas being released. After perihelion, as the object moved away and cooled, water vapor became more prominent while carbon dioxide declined. Taken alone, this shift might seem explainable. Different molecules respond to solar heating at different rates, so the chemical mix changing over time is not unusual. But here's where it gets genuinely strange. The metals. Nickel appeared in the coma, at concentrations that stood out immediately. This alone is notable. Nickel has been detected in other comets, but rarely at these levels, relative to the surrounding material. Then iron began appearing more clearly in the post-perihelion data. And here's what stopped researchers cold. The ratio between nickel and iron was far outside the range seen in solar system comets. In our own solar system's comets, nickel and iron appear in roughly predictable proportions, proportions that reflected the chemistry of the early solar environment where those objects formed. They're not identical across all comets, but they fall within a recognizable range. That range is one of the fingerprints scientists use to classify cometary material. 3I/Atlas broke that fingerprint decisively. The nickel to iron ratio was wrong, not slightly off. Wrong in a way that has no clean parallel in any comet studied before. The only natural environments where nickel appears so prominently relative to iron tend to involve extreme temperatures or highly processed material. Natural explanations exist, but they require rare conditions that haven't been documented in comets observed within our solar system. This places 3I/Atlas in a chemical category with no clear precedent. What amplified the strangeness was timing. The most anomalous chemical signatures didn't peak at perihelion, when solar heating is most intense and volatile release should be at maximum. Some of the most unusual readings became clearer after perihelion, when activity was supposedly winding down. In normal comet science, post-perihelion is the quiet chapter. With 3I/Atlas, removing the noise didn't reveal a simpler story. It revealed a more complicated one. But none of that, not the metals, not the ratios, not the timing, prepared scientists for what the methane data showed. The methane anomaly. Among all the chemical signals Webb detected, methane produced the deepest confusion. And to understand why, you need a quick lesson in cometary chemistry. Methane is what scientists call a hypervolatile molecule. It doesn't need much heat to start. Escaping from an icy surface, the slightest solar warmth is enough to drive it off. Because of this, methane is expected to behave in a very specific, very predictable way. Appear early in the approach, peak before or near perihelion when heat is rising, then fade as the object moves away from the sun and cools. That's the textbook. 3I/Atlas threw the textbook across the room. During the early inbound phase, when 3I/Atlas was still warming up, when carbon dioxide and carbon monoxide were already clearly detectable, methane was nearly absent. This was already confusing. Methane is more volatile than carbon dioxide. If CO2 was outgassing, methane should have been impossible to miss. It should have been the loudest signal in the data. It wasn't there. And here's what nobody expected. After perihelion, as the object cooled and moved away from the sun, methane production didn't fade. It increased. Its concentration relative to water vapor rose to levels that made scientists stop and question their assumptions. Instead of following the established thermal model, appear early, disappear as heat drops, methane did the exact opposite. Methane grew stronger as 3I/Atlas cooled. That sentence shouldn't be possible. Scientists proposed explanations quickly. 1. The outer layers of 3I/Atlas might have been depleted of methane before we started observing it. Perhaps volatiles were stripped during the long interstellar journey, so methane only appeared once perihelion erosion exposed deeper, undepleted material beneath the surface. This is possible in principle, but here's the problem. Carbon monoxide is even more volatile than methane. It escapes at lower temperatures. If methane had been stripped from the outer layers, carbon monoxide should have been stripped too. But carbon monoxide appeared normally, early and on schedule. The depletion model collapses against that comparison. Another explanation, internal structure. If 3I/Atlas contains pockets of material thermally insulated from the surface, regions where heat takes much longer to penetrate, methane trapped in those pockets might survive the initial solar encounter and only begin escaping later as heat slowly works its way inward. Think of it like geological strata, where each layer has a different composition and responds to the same heat source at a different rate and on a different time scale. This would require an extraordinarily unusual internal architecture, layers with dramatically different thermal properties, sealed reservoirs that open only after sustained heating. It's not impossible, but nothing like it has been confirmed in any well-studied comet. And invoking such an exotic internal structure as an explanation starts to feel less like a solution and more like a new problem. Because now you have to explain how that structure formed, how it survived the interstellar journey, and why nothing remotely similar has appeared in 3 decades of detailed comet science within our own solar system. What the methane anomaly really does is attack confidence in the tools scientists rely on to read comets. Methane's hypervolatility is precisely what makes it useful as a marker. Because it's so predictable, its behavior tells you about thermal history. When methane stops being predictable, you lose one of your most reliable instruments for interpretation. And the methane anomaly doesn't stand alone. It stacks on top of the size revision, the motion problem, and the elemental ratios. Each of these in isolation might be explained away. Together, they form a pattern that resists any single framework. But there's one more piece, and it comes from post-perihelion data that wasn't supposed to be interesting at all. Post-perihelion pulses. What's still active beneath the surface? After 3I/Atlas began its outbound journey, something else refused to go quiet. Overall brightness dropped, consistent with a cooling object. Scientists were watching for exactly this pattern, the slow fade that signals the main event is over. And the fade came, more or less on schedule. But nested inside that general decline were pulses, subtle, repeated brightening events that didn't fully disappear. They showed up with a rhythm that stood out against the downward trend. Not chaotic, not random, but not cleanly explainable either. The simplest interpretation for periodic brightness changes is rotation. As a comet rotates, different surface regions with different compositions and activity levels move in and out of sunlight, producing measurable variations in brightness. It's a well-understood effect, routinely used to calculate rotation periods in comets and asteroids. Here's the catch. The timing of these pulses didn't align with 3I/Atlas's estimated rotation period. If rotation was the driver, the rhythm should match. It doesn't, or at least not cleanly enough to serve as a complete explanation. That leaves something uncomfortable on the table. Something beneath the surface was still responding to energy, even as the exterior cooled. Internal processes, perhaps delayed thermal conduction finally reaching volatile-rich layers deep inside, perhaps something about the object's structural heterogeneity, continued releasing energy in waves that the exterior calm was actively concealing. Think about what that actually means. Normally, post-perihelion is where the data gets simpler. Fewer active processes means fewer variables. The comet quiets down, and interpretation becomes easier. With 3I/Atlas, stripping away the surface noise didn't reveal a simpler interior. It revealed something still working, still active, still releasing energy through a mechanism that doesn't cleanly match rotation, outgassing, or any other standard explanation. The object looked calmer from a distance. The data said something underneath it was still running, and when you sit with that picture, a massive nucleus with anomalous chemistry, with unexplained motion, and with something unidentified still operating beneath the surface, the statistical question starts to feel unavoidable. What are the actual odds that this object is here at all? The statistical problem. Nobody is talking about enough. Step back from the individual anomalies for a moment, because there's a probability puzzle underneath all of this that doesn't get enough attention. In nature, small objects vastly outnumber large ones. This holds everywhere, in asteroid populations, in comet families, in stellar debris fields. It's a fundamental feature of how matter aggregates and distributes across cosmic scales. You expect to encounter many small objects for every large one. Based on this principle, astronomers expected that as detection technology improved and interstellar visitors began showing up more frequently, the first confirmed objects would mostly be small and faint, the most common category. You'd have to detect many small interstellar objects before statistically encountering a large one. But look at what actually happened. 1I/Oumuamua, small, elongated, unusual, but modest in scale. 2I/Borisov, comet-like, roughly 1 kilometer, fitting comfortably in existing frameworks. And then, with only the third confirmed interstellar object, a nucleus pushing 3 kilometers in diameter with chemistry unlike anything in our solar system's records. A multi-kilometer anomaly, third try. That's not what the statistics predicted. One answer is observational bias. Large active objects are simply easier to see. They reflect more light. They release visible coma material. They trigger alert systems that quieter objects never approach. If smaller interstellar objects are passing through silently, no coma, too faint for current surveys to catch. They could be slipping past in enormous numbers without leaving a trace. From this view, 3I/Atlas isn't unusual because it's rare. It's visible because it's big and loud. That explanation has real merit. But here's what it doesn't explain. Modern sky surveys now cover large fractions of the sky, repeatedly with increasing sensitivity. Even faint objects tend to leave statistical fingerprints, unexplained trajectory events, subtle brightness anomalies, indirect signatures that pile up over time. The near absence of such signals from smaller interstellar objects pushes back against the idea that they're simply everywhere and we're missing them. Another possibility, 3. I/Atlas belongs to a rare category of object that formed under unusual conditions, not representative of the broader interstellar population, but a genuine outlier produced by a violent or exotic stellar process that occasionally launches large, atypical objects into interstellar space. If that's the case, we got extraordinarily lucky detecting it this early, or unlucky depending on how much you enjoyed having your models intact. Here's another way to frame just how deep this problem goes. The Milky Way contains somewhere between 100 and 400 billion stars. Most of them, at some point in their formation and evolution, ejected material into interstellar space. Comets, planetesimals, asteroids, fragments of failed planets. The galaxy is seeded with this debris. Theoretical models suggest an enormous number of interstellar objects should be transiting our solar system at any given moment, with some estimates running into the trillions for objects in the kilometer-size range. If those models are right, we should be encountering interstellar visitors regularly as our detection capability improves. But if most of those objects are small, inert, and dark, no coma, no reflective surface activity, just cold rock tumbling silently through the void, current sky surveys would never catch them. They'd pass through at tens of kilometers per second and vanish before anyone had time to point a telescope. What we're seeing may not be a representative sample of interstellar space. It may be a filtered view, showing us only what's big enough, bright enough, or active enough to trip our instruments. And 3I/Atlas, far from illuminating what interstellar objects look like, may be showing us how distorted our view of them actually is. What we're left with. Pull all of this together, and you get an object that resists clean categorization at every level. Its nucleus is far larger than anticipated, carrying mass that breaks the models built to explain its behavior. Its motion shows non-gravitational acceleration that the observed surface activity can't fully justify for something this heavy. Its chemistry includes elemental ratios with no clear parallel in solar system comets. Its most volatile molecule appeared late and grew stronger as it cooled. the reverse of what thermal physics predicts. And even after perihelion, when everything was supposed to simplify, something beneath the surface kept generating pulses that don't align with rotation or any other standard mechanism. Each of these anomalies has a potential natural explanation. Scientists are actively working on all of them. No reputable researcher is calling 3I/Atlas artificial, but what the scientific community is acknowledging, carefully in the measured language of the published papers, is that this object doesn't fit any existing framework well enough to be fully explained by a single model currently on the table. That matters because frameworks are what science runs on. When an object fits a framework, you use the framework to predict behavior, trace history, extrapolate forward. When it doesn't, you have to ask whether the framework needs an adjustment, or whether the object belongs to a category the framework simply doesn't include yet. 3. I/Atlas is forcing that question, not because it's mysterious in a sensational way, but because it's anomalous in a systematic way. Every layer of analysis that was supposed to narrow, the uncertainty has instead widened it. Think about what that trajectory actually means. We've had 3 confirmed interstellar objects now. The first one, Oumuamua, confounded everyone. Non-gravitational acceleration with no visible coma, a shape unlike any natural object in our solar system. The second, Borisov, was reassuring. It looked like a comet, behaved like a comet, confirming that at least some interstellar visitors are familiar. And then 3I/Atlas arrives and takes a blowtorch to the reassurance Borisov provided. With each new detection, the picture should be getting clearer. Instead, it's getting stranger. That's the opposite of how science is supposed to progress. But here's what this actually means. These objects aren't selected. They're detected, filtered through instruments with specific sensitivities and specific blind spots. What we're seeing is not the universe. It's the universe as our current tools allow us to see it. The objects that make it into our catalogs are survivors of our detection process, not a representative sample of what's actually out there. If our detection process systematically favors the unusual, the large, the active, then our picture of interstellar space may be the most misleading kind of picture possible. It shows us the exceptions. The vast, quiet majority passes in complete silence. 3I/Atlas may be many things: a chemical oddity, a gravitational puzzle, a statistical anomaly. But perhaps its most important role is as a reminder that the map we've drawn of interstellar space has been drawn almost entirely in the dark, with instruments designed for a solar system, not for the galaxy it sits inside. The real question isn't what 3I/Atlas is. The real question is what it's telling us about everything we thought we knew, and how many more visitors are passing through in silence right now, invisible to every instrument we have, carrying information we haven't yet figured out how to ask for. If this hit differently than you expected, drop a comment below. Subscribe, because when the next Webb data drop lands, you'll want to be here for it.